Anthopoulos, who's a professor of material science and engineering in KAUST. He got his PhD from Staffordshire University. He worked as a full professor in Imperial College London. His research interests are diverse and they cover the development, application of novel processing and physics, chemistry, and applications of functional materials, as well as Professor Xiaohang, who's an associate professor of electrical and computer engineering and applied physics at KAUST. He got his PhD from Georgia Tech. He was one of Georgia Tech 40 under 40, and he received many awards. So please welcome our speakers for today.
Okay. Hello, everybody, and good afternoon, and welcome to the Sustainability Seminar series. So thank you very much for your very kind introduction. Try to see how I can do that. All right. So the title of our talk, Semiconductors towards carbon negative technologies, is a kind of an ambiguous title. We're not going to be presenting any technology that strictly addresses the carbon negative bit, meaning usually extracting carbon from the atmosphere, carbon dioxide, but we will be talking about semiconductor technologies that can contribute toward that effort, among many other things. So the talk is a two-part talk. We have part one, myself talking a little bit about an introductory bit on semiconductors, because I believe maybe a lot of you may not have the background on the topic. Then I will talk a little bit about electronic manufacturing and some of the big challenges facing our modern societies, and some of the research highlights coming from my group. And then I would hand over to Professor Li to continue with the topics on overview of important inorganic semiconductors. He talks about inorganic. I will have some organic, and I will explain what this means, and how these technologies can be used for a greener future and healthier future. And there is a few examples of how these technologies can be applied. So semiconductors, what we classified as semiconductors are typically solid materials where they exhibit electrical conductivity, ability to conduct electrical current, somewhere between classical metals, you see here on the left. We have platinum and gold. Copper is one of the best conductors that we have. And the very insulating materials, such as ceramics and plastics. So semiconductors are those materials that actually exhibit conductivity somewhere in between. And you see the conductivity there is a logarithmic scale. It goes from millions or tens of millions of Siemens per centimeter to minus 18. So it's a huge difference in the conductivity. And semiconductors just in the middle. And there are many different types of semiconductors. We have semiconductors such as elemental semiconductors. Silicon, germanium are two examples where single atoms assemble and form crystals, and those crystals exhibit semiconducting properties. Germanium is the same, but we have also more complex form of semiconductors. The most conventional one, silicon carbide, for instance, but we have a number of other ones, gallium phosphide, gallium arsenide. There are many different types. We also have organic semiconductors that I will be briefly talking about today. These are semiconductors very different to the traditional semiconductor list in this table, are materials that actually consist of molecules, assembled of molecules that form crystals. And unlike elemental semiconductors, where the atoms in the interaction between the atoms define the electronic properties of the crystal, in organic semiconductors, we have essentially a single molecules or chain of molecules defining the overall properties of the crystal. So molecular semiconductors often referred to also as well as organic semiconductors. And there are advantages and disadvantages with all different classes. From our side, we've been exploring organic semiconductors because they take very little energy to make, unlike silicon that you need to melt down 1,000 degrees Celsius. And then they can take a little energy to also fabricate functional devices through high throughput manufacturing, something which is not the case for silicon, for example. However, suffer from poor performance. And I will tell you a little bit about what we've been doing to improve those characteristics. What is important about these semiconductors is that we can tune the chemistry. So in the case of silicon, we can dope it with foreign atoms, boron, for instance, and make it highly conductive. Or introduce other elements like oxygen and oxidize silicon and create silicon dioxide, one of the best dielectrics. So essentially, by chemical modification, we can span the electrical properties across the entire range we see there. And this is what makes, for example, silicon the magic material, a material that comes with all these interesting characteristics, and which essentially has is the reason why it dominated the silicon of the area of microelectronics. So what do we do with these semiconductors? Just a kind of a snapshot I found on the web is shown here. On one upper half of this diagram, we have the compound semiconductors. These are important materials that are known for a long time, a lot of them, and recently found a lot of uses in applications such as electrical vehicles, because they can handle a lot of power. Telecommunication is another example. My phone has silicon as well as compound semiconductor electronics when it needs to communicate with a base station far away, because it can deliver the necessary power, while silicon struggles. Then we have the world of silicon, which is very well established, and we have applications spanning from energy generation, photovoltaics, the main technology used today, all the way to Internet of Things, things that are interconnected. It can be sensing nodes, it can be our mobile phone or telephones or TVs. Everything becomes smarter and smarter. So these emerging Internet of Things device ecosystems start becoming very diverse. And there is a problem with this, because we end up with a lot of electronics that need to be manufactured, but also then disposed. So handling and managing this is becoming so-called e-waste, becoming a major hurdle, a major topic of discussion and research and development in recent days. So this is a kind of what has been happening with it, that kind of a cloud of Internet of Things device ecosystem. We see essentially a huge market, hundreds of billions. But most importantly is the growth rate these markets are experiencing. We're talking about 38% or so. So it's rapid, it's essentially exponential. So we are just a matter of time before we start seeing serious challenges appearing before our eyes, not only of looking at the market, but actually how we handle all these electronics that being produced within this device ecosystem. And to understand the problem a little bit more, I will just walk through the brief history of electronics. This slide I have prepared a few years back for essentially for people that are not coming from the area. This is kind of 120 years history of electronics, starting from vacuum electronics, so-called tube rectifier. This was a big devices, essentially consist of metal plates and evacuated from any gas, and electrons could fly from one direction to another, but not the other way around. So they were used at the first generation of electronics, but they were, of course, very fragile and consume a lot of power. Then we have the advent of transistor, the first solid-state crystal-based semiconductor-based transistor, where with a very little signal, you can actually switch a large current. That was a perfect amplifier. And of course, we had the integrated circuit, and fast forward to today's state-of-the-art microelectronics, where if you take your state-of-the-art phone and you dissect it, what you will find inside is the building blocks, the transistor in its latest form, so-called FinFET. It's a three-dimensional device. It's very tiny. So if you dissect it, cross-section it there, what you will see is you will see the cross-section of the fin. And what you can actually do, you can count the silicon atoms from one side to another. And we're talking now about nodes, the so-called these critical dimensions, down to 5 nanometers. And if you assume that an atom is kind of a 0.1 nanometer, so we only have a handful of atoms from one side to another. So it's truly nanotechnology in action. But in doing so, we encountering a lot of hurdles. And one of them is the so-called Moore's law. The Moore's law dictates that this number of devices we place every square inch of chip or a unit area doubles every 1.5 to 2 years. And this is exactly what's been happening. Making the transistor smaller and smaller through this extreme downscaling enable us to put more transistor per unit area. We are now at a point, starting from few tenths of thousands of transistors back in the 90s, we're now to a point where we have 1 billion transistors per square millimeter. So in a single microchip in your mobile phone, and there's not only one microprocessor in there, we have tens of billions, several times the population of Earth. And this, of course, has enabled us to have such an immense amount of computing power in our fingertips. It also enables a lot of other things. Enable, for example, through touch screens interface with the machine in ways that we never experienced before. And all these are very recent. I remember the first iPhone. It was mind-blowing. The next best thing before that, the thing better than that at the time was the Palm we had, where we had a stylus interfacing with the machine. But apart from that, it was all mechanical type of buttons. But going this direction has also created a lot of issues. Building a factory that is able to handle 5 nanometer feature devices costs 10 to 20 billions. The previous generations were only a few billions. So essentially only a few manufacturers are able to produce these microchips at a very great cost. And this manifests dramatically on the carbon emissions of these products. So this is an example from Apple, but there's many other similar examples, where essentially what you see here is split between the manufacturing and the product use emissions. And you will see the manufacturing, just the integrated circuit alone, takes nearly 40% or more of the total carbon emissions. And then we have the use, software updates, and all these things during the lifetime of the product that's also contributing. But the vast majority comes from the manufacturing, the hardware. So we have the microprocessor, and I said many in a single phone. We have the display, electronics, steel, the various metals that have been used to make that. So essentially, we have a major issue with the state-of-the-art chips. And these latest chips, the first application is these high-end mobile phones. Is always the best chips that exist out there because it gives us more computing power. If we now split the devices to those which are permanently connected, like a desktop or this screen, for instance, compared to mobile phones and other battery-operated devices, we see that in the case of battery-operated devices, the majority of the carbon footprint comes from the production, this dark color here, while use takes only a small part. If we move to connected devices, then you see use is very demanding, become a critical issue. So this, of course, is associated with the fact that these type of devices require batteries, require more hardware that goes into there, and of course we need to still power them with some sort of source of energy. And if you now do a little bit more and we analyze essentially the carbon footprint during use and during production, you will see that in the case of always connected devices, the use becoming the dominant factor. So we have to make more efficient devices, but of course this is kind of not easy to do because the better the microchips become, the more capabilities they provide us. So we tend to use them more, etc. While the battery-operated devices are mainly the carbon footprint is determined by the production process. So there's a lot of improvement on improving the manufacturing, but also improving or making the energy we supply in order for this device to be operated become more green. So improvements can be done in many different fronts. And this is a very good example how shifting from polluting technologies to more green technologies can have an impact. Essentially, we have this breakdown from AMD, a very big company in the area of microelectronics, where essentially if the energy comes from coal, then of course the carbon footprint associated with the use of the device is very huge and surpass that of the actual manufacturing. But as we transit into more green technologies, renewable energy sources, we see here, for example, wind, also nuclear is pretty good at that, solar, etc. Then essentially we have a system or a scenario where most of the carbon footprint is dominated again from manufacturing, by the manufacturing components. So the challenge there is how do we improve manufacturing and how to develop better renewable technologies. And this is where semiconductors can come in and play a very big role. So this is my final slide on this type of analysis and shows essentially what we predict in less than 10 years from now. The information and communication technologies energy projections, essentially the electricity demand, can be as high as 20%. So this ICT sector is a really important piece of the puzzle that need to be addressed if we really need to have an impact. And clearly, to me, is that producing energy using green technologies is a priority. Coming up with a better manufacturing is also critical. But silicon has invested, for instance, 60 years in this industry. I don't think it's going to get simpler. But there's a lot of other emerging electronics that could well dominate our surrounding. And those electronics perhaps could be manufactured using much more green technologies. And this is exactly what we've been doing or trying to do in my laboratory. So this is the two topics we're trying to address. One is coming up with a greener technologies, and one is coming up with more environmentally friendly manufacturing technologies. So this is global energy consumption by source, and you will see that how long we came from the 1800 to 2019. We have essentially 140,000 terawatt hour, and only a small blip there is actually covered by these renewable energies, and among them is solar. Now, if we look what is happening today in solar, what you will see is that we have different generations. The first generation dominated by silicon, gallium arsenide, there are many other technologies, but silicon dominates the power generation when it comes down to very large scale solar plants. We also have the second generation, thin film devices. You don't need to really make wafers, but actually you can process those on substrates at a much different, with a different form factor potentially. And we have the third generation, and this is where we are interested. I'm personally interested in these technologies, and this includes organic, perovskite, hybrid systems, dye-sensitized quantum dot, and various other inorganic semiconductor technologies. We are very much interested in organics because, as I said, instead of having single atoms forming a semiconductor, we have molecules. And what this enables us to do is to synthesize a lot of different molecules. Essentially, the library of possible materials is infinite. We can come up with infinite number of possibilities. And what is the challenge is to identify the key properties and start designing the right molecules for the right applications. And it's not only for solar cells, it's for a lot of other semiconductor applications. One of the most important advantages of these emerging technologies is that they can utilize existing spaces. For example, can be integrated with buildings, like building integrated PV. KAUST is a perfect example. Imagine all the facades and all the glass surfaces could be covered by a plastic sheet of these renewable or energy harvesting devices, semi-transparent solar cells. And these technologies exist at a cost right now. So we have to really work to make them more efficient and cheaper to produce. This is where the challenges lie. But if we can do that, then we can see a lot of new application space being created for these emerging technologies. Another very recent and important finding is the carbon footprint of organic PV, for example. This is taken from a white paper from Heliatech, one of the pioneers in the field of organic PVs, which have analyzed one of the products, and they estimated that the carbon footprint can be as low as the hydro, the lowest essentially footprint available today. And this is not surprising to the people working in the area, because we can synthesize these materials with very little energy intake, and we can really manufacture the devices using low energy and greener kind of chemistry, if you like, and greener technologies. And if you want to compare OPD with other PV technologies, this is the comparison. And still we see that this organic technology can deliver real solutions with a very small carbon footprint when compared, for example, to state-of-the-art silicon-based technologies. To give you an example, the total payback time for a panel that's been based on organic solar cells has been estimated to be as low as a few months, as compared to a few years for silicon. So within months, essentially, you have a technology that produces energy for free. This is perhaps where the carbon negative comes in, Xiaohang. And I think this is an interesting aspect that hasn't been considered. So we're talking about completely different business models that should be developed around these technologies that are emerging. And if you see how these technologies are manufactured, is using printing techniques. Meters per second have been printed, nothing to do with the conventional inorganic technology. So this is the vision. Can we improve efficiency, and can we improve the method of manufacturing material cost? And this is a kind of a chart. It's a very busy chart, but it's a standard NREL chart by one of the institutes that actually benchmarks the performance and certifies the performance of different technologies. And they have grouped here the first, second, and third generation. And what we have down here is the organic solar cells, where during the last 5 years, we've seen a jump from 12% to around 20%. And this is where we've been a few years ago from KAUST Solar Center. We managed to demonstrate now we have more efficient devices, but breaking the 18% efficiency, so essentially taking 100 photons and converting this 100 photons to 18 electrons, it's one of the best performance. It was the best performance at the time. Right now, organic can deliver just above 20%. So essentially reaching levels which are been reached by silicon, around 24 for single crystalline wafers. But if you go to more complex structures, this efficiency can, of course, increase, but at a cost. Organics, potentially we can do that using very inexpensive, very upscalable manufacturing technology. So we minimize the energy intake for making the material, but also the energy that it takes to produce the final product. So in my group, what we do, we take these technologies, we zoom in, and we isolate this big, nice, interesting design of organic photovoltaic, which are semi-transparent. And we can actually, if you zoom in, you will see a single photovoltaic cell. What this organic photovoltaic cell usually comprises of is a kind of a multi-layer stack. This thickness is no more than 150 nanometers, very, very thin. So we have essentially the so-called whole transport layer. This is the positive charge, which is extracted out of the device. This is the photoactive layer, essentially absorbs the light and generates the charges, the electrical charges that we extract from the corresponding electrode. This is the holes and this is the electrons. And essentially, the cell acts like a battery the moment that is in the presence of light. So we've been working on improving the photoactive materials, but also improving the electron extracting and the hole extracting, the positive and the negative charges extracting layers, which play a very important role both for the manufacturing and the efficiency of the cells. So one important highlight from this topic is that we recently been able to use single monomolecular self-assembled layers. Like biology takes single atoms and makes builds us. In a way, we took a single atoms which are engineered to functionalize, to essentially react with the surface of a specific electrode. And you essentially place the liquid there, and this molecule will self-assemble next to each other, forming very dense monolayers, which are only like a nanometer thick. So essentially, we have managed to replace the traditional whole transporting layer, which is typically 30, 40 nanometers thick, with something which is 1 nanometer. So essentially minimizing the material by a factor of 30 to 40, yeah, the amount of material used. Plus, we have been using nature for this self-assembly. We don't use sophisticated equipment to grow this material where we want it to grow. And using this self-assembled monolayer as the active components, we've been able to make solar cells which are 18% efficiency. So essentially 18% of the solar spectrum can be converted, the power from the solar spectrum can be converted to useful electrical energy. What we also identify is that once we use these single atoms, single molecule layers, you can actually start thinking of recycling and reclaiming and reusing part of that cell, because these monolayers are actually very gentle. They functionalize covalently very strongly on the surface of this electrode, but they don't damage it like other technologies do. As a result, you can potentially take the substrate, remove all the metals and reuse them if you want, but also take the substrate, which is the largest part of the volume of the material we're using, the plastic substrate or paper or glass we're using to build these devices on, are essentially millimeter thick when compared to a few hundreds of nanometer of the active layer. So it's only being able to recycle part of that device is very important and reuse. And we have shown this is possible. You can do it several times. Essentially, imagine a scenario where you take the solar panels and you recycle major part of it. You take the active material, separate them, and reuse them with a minimum energy input, the whole process, and producing again a fresh panel that you can manufacture with a very small carbon footprint. So this is a vision of the future that potentially could materialize or enabled by these organic semiconductors. Instead of in addition to the interlayers, we also work on the photoactive layer. And what we do there is trying to improve the efficiency with which converts photons to electrons. And one way we have identified was quite interesting is to add small molecules as a third or fourth component in that blend of semiconductors, which is rather complicated in the case of organics. But what we found is that by adding this small, what I call salt and pepper in our devices, we can improve, tune the performance of these devices. So if we take a device which has an efficiency of around 17%, you add this tiny amount of this small molecule, which is essentially an electroactive molecule, acts like a dopant, induces a charge, but also modify the microstructure of the semiconductor. We can increase this peak performance to over 18%, 1%. It may not sound exciting, but imagine this 1% extra during the lifetime of that product generating excess power, plus improves the stability of the device. This is another finding we came across. So that's exactly what we did. And using this added technology, we're able to push the efficiency beyond 18% of these solar cells. I'm switching gear now, and I'll tell you, I have a few slides about the effort we've been making to address the manufacturing issue for electronics. This is already, you've seen the Moore's law, and we're already in the hyperscaling era. Essentially, we're pushing the scaling to a point where single atoms start making a difference. And the process falls apart. And this is why the cost per transistor in recent years has been increasing, was always reducing over time, and only now start increasing because it takes a lot of effort, energy, and money to make them. And of course, that has a negative impact on the carbon footprint of the technology and the manufacturing thereof. What we've been doing is to look at different types of electronics. I've shown you about the conventional electronics, but at the same time, we have different concepts and different forms of electronics emerging. For example, probably you heard about quantum computing. It's a very important technology, potentially could solve a lot of the issues in terms of computing, but most likely these machines will be hidden in the cloud, performing very demanding computation. We also have neuromorphic, essentially going away from this number crunching digital technologies to something is more analog, more like a human brain. Already neuromorphic engines exist in microchips, and industry learns from these products and how better to be implemented. What I'm very interested about the new forms of electronics which take different shape and size. Big screens is a new form of electronic, emerged only in the last 20 years. Before that, it was bulky CRT tube screens. Now we have flat panel screens. So it's one example of such technology. And how this future electronics will look like, just try to summarize here, will be very different. They'll be flexible. We're already seeing the first products, foldable screens and foldable electronic gadgets like already exist in the market, all based on organic plastic electronics. We will see even soft electronics or even transient electronics that can be implanted in our bodies, perform a function, record a signal or deliver a drug, and then dissolve away after a pre-programmed time. And this already been demonstrated, proof of concept. So there's not really anything to make me believe that's not going to happen. And all these new developments will generate a lot of new opportunities. We will have essentially, hopefully, this new industry will come with more environmentally friendly character and more sustainable in manufacturing. And we'll see, hopefully, this type of manufacturing changing, going lower energy in terms of intake and carbon footprints. But there is a problem, because how to get the necessary performance. But if we manage to get there, then we will see a lot of new applications. So potentially we'll see already happening with the flexible electronics. If we fast forward 5-10 years from now, you will see a lot of new functionalities added on those initially very rudimentary, very basic electronics. And this new functionality will enable a lot of things, a lot of potentially health applications, among many other and vision applications. And this will, it's my voice. And this will lead to essentially at some point technology proliferation. So we have essentially the platform technology that can be used for many different things. People envision even pills with electronic functionality. Already exists some prototypes, but what they can do is very limited. But all these start becoming a reality, from kind of a Star Trek technology into real accessible technology. But together, you need the performance. And that will require transition from the conventional silicon to these new forms of industries in electronics. But the moment you do that, you pay a penalty in terms of performance of the device, to a point where these emerging electronics are nowhere close in terms of performance to the silicon electronics. This is the so-called performance gap. what I want to call. So we ask ourselves, can we actually come up with new manufacturing ways and access the critical small dimensions that silicon has access over these years, but using much simpler approaches, manufacturing approaches. And that's what we've done. To understand the challenge, this is the length scale in nature. Single atoms as biology through natural self-assembly can do that. We know it's possible, but how probable? If we look at the technology we have available, you'll see that not a single patterning technology, manufacturing technology can span across all these length scales. So we have essentially a gamut, a library of technologies that complement each other. So we go from large area photolithography printing, all these electronics I've been showing you. I can go down to a few micrometers, but if we want to go down to nanometer, we have to really go to very expensive, very energy intensive technologies. And this is where the gap exists in terms of performance. State-of-the-art electronics, large area, new forms of emerging electronics. And that's something of a big issue because these technologies cannot talk directly to silicon. So if I make this printed electronic circuit, I will, at the end, I will have to pick and place a silicon microchip in order to enable connectivity with a base station. That's not a solution. We don't get rid of silicon. Ultimately, we would like to get rid of silicon altogether. And but how do we do that? How do we make these devices being well performing? So we've been developing patterning technologies, and this is a few slides I have left, which combines essentially large area processing capabilities with the ability to shrink key device dimension down to a few nanometers. So what we have been developing is one of the examples is the adhesion lithography, ELITH, we say. We only use very, very relaxed lithographic steps, which are scalable to meter squares of substrates. So it's absolutely inexpensive. And then in combination with a bottom-up technology like letting nature take charge of how these materials self-assemble in pre-programmed areas can then define key feature dimensions, which are down to 10 nanometers. So essentially, this is two metal electrodes we have patterned using this technology, only 10 nanometers apart from each other. And now what we need to do is to place a semiconductor in between them and start essentially creating functional electronic devices. And these devices can take many different forms and shapes. We have been making nanogaps, which are essentially interdigital electrodes, which are, although electrodes are separated by a few tens of nanometers, the electrodes can run along each other for hundreds of meters. So essentially, the small size is connected to the macroscopic world. So we have a nanoscopic dimension, but the device itself is big. And what this enables you to do is to essentially create devices which are performing, the performance on par with silicon electronics. And I'll show you one example. Another way we have actually found how to utilize even more efficient, energy efficient manufacturing technologies to combine these nanogaps. I've shown you this is essentially the same structure shown here, and place inside there a precursor material, not a semiconductor, but it's precursor, which is easy to process. We have water soluble precursors, so very environmentally friendly, unlike silicon that you need to grow with sophisticated methods. We can place it there and then take a big flash lamp, exactly the same technology we're using for the flash photography, the flashlight. And this is the machine we have. You shine, you flash the whole structure, a millisecond of intense pulse of light. And what we discover is that the metal absorbs part of this light and they heat up momentarily, just for a few milliseconds. But the heating up, it can reach temperatures up to 500-600 degrees Celsius, which when we put them very close together, they will start coupling temperature from one to another side of the two electrodes and converting the precursor material in there to the stable phase, which is the semiconducting phase. So essentially, you're performing chemistry within a few milliseconds, but using very little energy. So essentially, and you can do that on inexpensive substrate technology. You don't need to have silicon or glass. It can be done on plastic or paper. So it enables us essentially to use low energy technologies to produce something which is quite a sophisticated. And what this little dimension, the distance between electrodes, allows you to do is to create devices which are very fast. And one of the key parameters is the operating frequency, how fast you can switch on and off these devices. And this is gigahertz. 1 gigahertz is 1 billion times a second. And essentially, if you can reach 5 gigahertz, you're already in the 5G telecommunication spectrum. Suddenly, your technology becomes relevant to 5G devices we have. And if you push it more than 90 gigahertz, you're entering the 6G, what essentially will be coming in 10 years from now. So suddenly we have a large area footprint devices, which can, the way we manufacture them can make a big difference in terms of performance. Suddenly we don't need this expensive equipment. Silicon industry has been utilizing over the years to produce what they have done. So what are we doing now? We're trying to combine all these technology and materials and production technologies and create so-called circular electronics that require very little energy to produce. We can satisfy the performance requirements for deployment in practical applications. We working on energy harvesting, new materials, and how we can combine this to create Internet of Things device ecosystems, sensing nodes, a number of things, but also how we manufacture, how we put all these components together in an energy efficient manner, and how then the end product actually can be utilized with the highest efficiency, and at the end, potentially be disposed, reused, or remanufactured, or refurbished, or recycled. So many different scenarios. We don't know what exactly going to be prevailing, what will be the dominating scenario, but I think will all be determined by a combination of the technology we're going to be using. So coming up with new ideas is definitely possible, and there's a lot of room for improvement there. So I will stop here, and I will let Xiaohang continue with his part.
Hello. Yeah, great. Yeah, thank you very much, Thomas, for the wonderful presentation. Here's the point. Okay, great. So, just following his excellent talk, I'm going to talk a little bit about inorganic semiconductors, right? So, for those of you who are not familiar with semiconductors, so we have organic semiconductor, which Thomas had talked about, but we also have inorganic semiconductors, such as silicon, that are very important to the modern society as well. And then I will first have an overview, and then I will narrow down to the wide bandgap and ultra wide bandgap semiconductors, because they are the so-called immersion technologies for the higher energy efficiency of the human society, and also enable us to have a healthier society in the future too. So this is like a brief history of the inorganic semiconductors. So the advent of semiconductor actually started in 1947 when scientists at Bell Lab invented the first transistor based on germanium. And then the silicon and germanium together are so-called first wave of semiconductors. So today they are used, as Thomas mentioned, people are manufacturing, billions and billions of transistors per year. Actually, the number is about 10 to the 23, 10 to the 22 transistors per year. So that's a few hundred trillions of transistors per second, right? So they are used in computing, memory, imaging, as well as the first generation solar panels, as Thomas mentioned earlier. The second wave, as you go, elevate the bandgap of the materials, is the 3-5 semiconductors. So the bandgap actually corresponds to a few different things. First is the photon wavelength that the semiconductor can emit or absorb. And the second thing is that how much voltage or how much power can it sustain. Okay, so as you go to larger and larger bandgap, you have a larger and larger power capability, and then the light the semiconductor can emit or absorb also become shorter and shorter, right? So as we go from silicon to 3-5 semiconductors, we suddenly have these wonderful materials that can emit light in the so-called telecommunication wavelength. So actually right now, the main reason that we can have this global internet connected by optical fibers around the world is enabled by the 3-5 semiconductor, because it can emit light that can be absorbed very little in the optical fiber. So it can travel in very long distance from point A to point B around the world. And so they are mainly used for telecommunication, but also for the autonomous driving. The 3-5 semiconductor laser and photodetector are used as sensors. And then, it comes to the focus of my talk. That is the advance of the wide bandgap and the ultra wide bandgap semiconductors. So the wide bandgap and ultra wide bandgap semiconductor have a much larger bandgap, like above 3 electron volts, right? 3 to about 6 electron volts. And that is much bigger compared to the 3-phi and silicon. So this enables them to be able to emit light in the visible and as well as the UV spectrum, right? Talking about the visible spectrum, a couple of weeks ago, we had this Future of Semiconductor Forum in Riyadh, organized by us, KAUST, and also RDI. And we were actually fortunate to have Professor Shuji Nakamura as one of our plenary speakers. And he is actually one of the inventors of the blue LEDs. And actually right now at KAUST, in this room and also outdoor, most of the artificial photons at night are from the blue LEDs. So, and this blue LED has very high energy efficiency. It's about 90% compared to 1% of the so-called Edison light bulb, right? So this actually has cut down the energy consumption of KAUST and also the entire world significantly, because about 20% of our energy consumption is lighting, right? So, and also many of the high-end display today, such as this Apple display, which costs a few $1,000s, is also based on the blue, is based on blue and RGB LED, including the blue LEDs. And then, moreover, the wide bandgap and ultra wide bandgap semiconductors, they can, like I said, they have larger bandgap, so they can handle much higher power, for a greener future, which I'm going to talk about later, and also better connectivity beyond 5G. And moreover, because they can emit and absorb the UV light, they can be used for the prevention of future pandemics, and they can be used for sensing and space exploration as well. So another application of the wide bandgap, ultra wide bandgap semiconductor is that they can be used as the host and photonic platform for the quantum information science, including quantum computing as well. So if the quantum computing materializes, they will, save a lot, significantly, a lot of energy compared to the conventional computing that we have today, right? So as a result, because of the importance of the wide bandgap and ultra wide bandgap semiconductors, most of the funding agencies in the United States, European Union, Japan, China, and other countries are investing heavily in these areas. And also, most of the large technology companies in the world today, including Google, Apple, Tesla, Meta, Intel, are investing in this area for those very important applications. Oh, okay, great. So because today we want to focus on the sustainability, so I'm going to talk about two aspects. One is the wide bandgap semiconductor for a greener future, and also the UV photonics based on those semiconductors for healthier future. So let's talk about the electric car, right? So electric car is said to be the mode of transportation for many people in the next few decades, right? So this figure basically shows the market share of the electric cars. By about 2030, we'll have about 25% electric car. And if you have read the news from the Saudi government recently, actually the city of Riyadh will target 50% electric car by 2030, right? That's a very ambitious goal. And also, like, this news just came out a few days ago that actually Saudis show very strong appetite for EVs. About 20% of the surveyed Saudi household say that if the EV is available and if they have the charging station, they will buy EV right away, right? So this is this not only happened in other countries but also here in Saudi Arabia too. But what is also very encouraging is that recently, also a few months ago, the Lucy Motors, which is a US-based electric car company right now, but majority owned by Saudi investment. They announced that they are going to have a factory with about $3.4 billion investment that to make about 150,000 electric cars in the King Abdullah economic city, right? So that's just 20 minutes away from KAUST. So if this factory becomes successful, I would imagine that some of my students and also could be many of the KAUST students who work in this place, right, to produce the next generation electric cars. And so what is the fundamental difference between a gasoline car and an electric car? Actually, that is about the content of semiconductors, okay? And for a gasoline car, on average, right, you have about 1% of the cost structure, due to the semiconductor components. But that percentage will jump to about 20 to 30% for electric cars, right? So essentially, the electric car is like a big iPhone with 4 wheels, right? So just like most of the smartphone today has a very high portion of semiconductor chips in the cost structures, and and one of the biggest difference between the gasoline car and electric car is that for electric car the powertrain is totally different. For electric car, the powertrain will be fully electrified, right? So this is a very simple comparison, right? So we can have a plug. This is connect to the rechargeable batteries, and that battery will feed the motors right here, right? But in reality, it's a lot more complicated, right? So this shows a more complicated diagram of the electric car actually powertrain, right? So electric car, here is the grid, right? 20 volt right here, 110 volt from the United States and different places. So this will go through an AC to DC inverter, and then this will feed, to the battery, and then and right here, and for charging, and then for the motor, the battery will feed the electricity through this DC to DC inverter to this high voltage DC bus, and then this one will further go to the low voltage battery or to the high frequency electric motors, right? And so all of these DC to DC, AC to DC, or DC to DC inverter or converter are all based on switching, right? If you are familiar with the circuits. And for switching, so it is very important for us to look for very efficient switching technology, because that will save us even more energy and reduce the carbon footprint. So let's look at this switch. This is a mechanical switch that all of us are very familiar with. Actually, in terms of switching, in terms of in terms of you want to make the switching when it's on, it's truly on, right? Truly on means that it will behave like a conductor or even a superconductor. So there's no obstacle for electron to flow from one place to the other. And when it's off, it is actually also truly off, right? Just like you have an insulator. So there's no electron flowing at all, right? So actually, electrically, this is a very ideal switching. However, this switch is not viable for electric cars, because for electric car, you need very high speed switching. So a typical, electric motor of Tesla, for example, require a switching at frequency about 10,000, 1,000 to 10 million switching per second, right? So even I think at this frequency, I think none of my students would like to do it because they are not capable to do it, right? But even if we hire probably the fastest, animal, on the earth, this is a hummingbird. The winds is only, swing at about 200 hertz at maximum, right? So in this case, we can no longer use the mechanical switching, but we need to use the transistors that can offer very high speed for the electric vehicle applications. Otherwise, if you have a very slow speed switching, your electric car will move very, very slowly, right? So that will be the purpose of having a car. So there are, in the pursuit of the ideal switch, there are a few things that we want to do. First is that we want high efficiency switching, right? Because I want to drive longer distance. Second is that I want high voltage switching, because that will enable us to charge faster, right? Right now, one of the biggest obstacles of electric car is that the charging can take hours to finish, compared to just a few minutes in terms of gas flowing for the gasoline car. And moreover, we want faster switching, because that can offer me more horsepower to carry a larger number of passengers within a certain volume. And next is I want high power density switch, because I want lighter car, and lighter car will translate to less energy demand and then less carbon footprint. Another one is that I want this switch to withstand extreme environment, right? I want this electric car to operate not only in the summer of Saudi Arabia, but also in the winter of some countries in the north, for example. Moreover, I want to have long lifetime, right? I don't want to change all the switches in my car every 2 years. I want my cars to run as long as a gasoline car, ideally 10 to 20 years, right? So all of this is actually not easy. And today, actually, the most common technology is based on silicon. And for the silicon MOSFET, which is transistors, it can do a lot of job well, but the energy efficiency is still quite low. Right now, for the average electric car, it can only convert about 77% of grid power to the power at the wheel, right? So this is already much higher compared to gasoline car, because for gasoline car, this conversion efficiency from gasoline to power at the wheel is about 20%, right? So this is already very high. But however, this still means that you will lose about 23% of energy in all doing all of this switching. So this is how the wide bandgap and ultra wide bandgap semiconductors, such as silicon carbide, gallium nitride, gallium oxide, aluminum nitride, and even diamond, can play a very important role. Let's look at this figure here. It's actually the most important figure for the power electronics industry. So basically, what this figure says is that for different semiconductors, such as silicon, gallium nitride, silicon carbide, and so on, how do their resistance change versus the breakdown voltage, right? Ideally, you want a switch that has very low resistance, so the electron can flow without any problem. So right, so you want to go as low as possible, right? You can go as low as possible right here, like vertically. But in the meantime, you want to operate this switch at higher voltage, so you can realize a lot of the benefits I said earlier. So you want the switch to operate, as high voltage as possible. But oftentimes, for most of semiconductors, you cannot achieve both at the same time. But for silicon, for example, for this resistance, which is about 10 to the power 0, right? It's about 1 milliohm centimeter square. For silicon, it can only handle about 100 volts. However, if you move this laterally to gallium oxide, it can handle 2 orders of magnitude higher, right? About 10,000 volts. So this indicates that this material can operate at much higher voltage for the electric car applications. And how about at a certain, at a fixed power, at a fixed voltage? Right? For example, if you want to operate your electric car or any electric equipment at 1,000 volts, right? Essentially, for example, if you use silicon carbide SiC, you can realize about 3 orders of magnitude less resistance, right? So because the loss of energy is proportional to the resistance. So this indicates that the wide bandgap and ultra wide bandgap semiconductor can save you 3 orders of magnitude less, energy compared to silicon technologies. So as a result, as I said earlier, many of the large companies are deploying this technology. So when Tesla was launched its Model S back in 2012, the power inverter in the motor was still based on silicon, right? But 5 years later, in 2017, Tesla, made its first inverter based on silicon carbide right here. So you can see that it can cut down the volume of this inverter significantly, right? This is because silicon carbide has lower loss, and therefore it has less heat. If it has less heat, it will require less cooling units, right? So, and then you can also make sure that you can run your car even in longer distance. So here is a comparison, like more quantitative comparison for silicon power units. It is about 70% more. Will consume 70% more power compared to silicon carbide units, right? So by using silicon carbide, which is a wide bandgap semiconductor, you can save 70% of energy compared to silicon. But you can also note that silicon carbide is just in terms of the capability, it's the lowest compared to the other ultra wide bandgap semiconductor. As companies progressively transition to larger bandgap power electronics, you can see an even bigger reduction of the power consumption or the inverter loss. Thanks. Yeah, and talking about applications, here is a very quick figure here. So depending on like there are many applications that use electricity today, right, as we all know. And from low to high voltage, you can see how different semiconductor can play a role, right? For lower voltage application, such as display drivers and DC to DC converter, people can still use silicon. But as you go to higher power and higher voltage, people such as for electric cars and ships and power grid, people will gradually shift to larger and larger bandgap material because they can handle the electricity at higher voltage and power. So the electric car is just the energy saving of power electronics for electric car is just a very small portion of the potential that can be brought by the wide bandgap and ultra wide bandgap semiconductors. So this is a prediction for the United States. So if people predict that if in electric cars, if all these power electronics units are replaced by gallium nitride, okay, we can save about 1.3 terawatt hour per year, right? But moving car is consume a lot of energy, but for industry it consumes even more energy because whenever you move things, right? Whenever you move big equipment materials, it consumes a lot of energy as well. So for the industrial motor drive, when people replace silicon by gallium nitride, you can save about 207 terawatt hour per year, right? And also in addition, you can save a lot of power from the solar inverter as well as the data server power supply as well. So all of these, the annual US saving of energy, if using gallium nitride alone, is equal to the power output about 318 average coal power plant, per year, right? So this is significant amount. If we use this technology, we can cut down the carbon emissions significantly. And this saving is also equivalent to the 40% of annual energy consumption in Africa as well. So this is a huge amount of energy saving. And this is the United States alone. As you know, in Saudi Arabia, I think we rank very high in terms of the energy consumption per capita. This is because we are moving air constantly, right? We are moving air constantly for all the buildings. That's air conditioning. So if in Saudi Arabia we can in the future and we can employ some of this technology, I can see a lot of the power saving as well. So after the discussion of the power efficiency, I want to briefly talk about how the ultra wide bandgap semiconductor, especially the UVC photonics, can be employed for a healthier future, right? So the COVID-19 pandemic is a wake-up call, right? It's a wake-up call because from the day that we know the pandemic is coming, we start to realize how important the indoor environment is, right? So our ancestors actually started indoor life about 170,000 years BC. And fast forward to today, in the United States, for example, people on average spend approximately 90% of their time indoor, right? So the environment indoor is very critical for our health. And talking about the recent pandemics, right? Actually, this is a huge challenge for the human being, especially the health of the human being. So this shows, the major pandemics since 1981, where we have the HIV, and to today we have had, tens of millions of deaths and also countless number of disabled peoples. And many experts in the field predict that we will continue to have epidemics or pandemics in the future as we witness a population growth as well as more interaction with wildlife, right? So how can we do? How can we still live as normal as possible? So I think like many people agree that we should assume that the pandemic will happen, and so we should get prepared. So before and after the pandemic starts, and we should pay attention to our personal habit, right? Wash hands, wear masks when there are lots of people, etc. But for us, we can focus on the transmission control. And in terms of the transmission control, it is very important to know that for any human being, we are actually more quote unquote virus and bacteria than human cells. This is because we have about, for average adult, we have about 30 trillion human cells on our body. But in the meantime, we have about 39 trillion bacteria and 380 trillion virus on average adult, right? So as we move, from one place to the other, we are actually spreading all these bacteria and virus at the same time. And of course, some of the bacteria are good bacteria, but a lot of the bacteria and viruses are harmful and they are pathogens. And in our life, we actually live on a world of surfaces full of pathogens as well, right? We use airplane, we use door handle, taxi, and elevator. And actually, most of us will never sanitize those surfaces after our use, right? And we just keep using whatever is left. And in terms of, and also in terms of the air as well, most of the building in the world, including our beloved diner, do not have a proper air cleaning or air sanitation facilities. So basically, for a lot of the airborne diseases, such as Omicron variant of the COVID-19, they can spread in the air, and then they can create community infection very easily, right? So how can we solve this problem? Actually, the semiconductor can play a very important role here, especially the ultra wideband semiconductors. That is that we can use the so-called UVC light. So the UVC light is a very interesting spectrum because these photons can actually break the bond in the DNA or RNA of the pathogens, including bacteria and viruses. So this is an experiment done for COVID-19 virus. As you can see here, after 60 seconds with the UVC light, there's no more COVID-19 virus left, right? And moreover, the UVC light is not chemical and it does not leave any residue, right? For example, after all of us leave this room later, then we can deploy UVC light to sanitize all the surfaces and air here, and does not leave any residue. And actually, the people have been utilizing UVC light for over a century. Niels Finson actually won the 1903 Nobel Prize because he discovered that the UV light could be used to eliminate the skin tuberculosis bacteria on the human skin, right? So, and moreover, in many parts of the world, especially in the developed countries, the UVC light is now used widely in terms of the wastewater treatment before the water is, sent back to the nature. And in the United States alone, there are, about 115 billion liters of wastewater get treated by the UV light per day. However, in Saudi Arabia, we still have a lot of work to catch up. Right now, the wastewater treatment rate is close to zero in Saudi Arabia. Okay, that's something I think that's certainly not ideal for the sustainable growth of the society. And again, the COVID-19 pandemic actually increased the public awareness of the UV light significantly. In many parts of the world, people have utilized it to sanitize the airplane, buses, supermarket, mass, and subway chains, right? Because it is very effective. It does not leave any residue, and it can do the job very quickly. And however, there is a significant drawback of the UVC technology today. That is because most of the UVC light today come from the mercury lamp, right? The mercury lamp, just from the name, that it actually contains mercury. So it is actually toxic, but also it's bulky, it's fragile, it has a short lifetime. And yeah, sure. And as about one mercury lamp contains about 10 milligrams of mercury. That can contaminate over 3,000 tons of water, right? So that can create significant damage to our environment. And as a result, there is a global push to phase out the mercury lamp. About 140 countries, including the top 3 economies in the world, as well as Saudi Arabia, have signed this Minamata Convention on Mercury to phase out the mercury lamp by 2030, right? And so if we want to get rid of the mercury lamp, how can we replace it? Actually, the UVC LED based on the ultra wideband aluminum gallium nitride semiconductor is the only known technology that can replace the mercury lamp in massive scale. And if you compare the UVC LED and mercury lamp, so it is eco-friendly, it is robust, and it has a much longer lifetime and a very small size as well. Actually, I used I used the real size of the mercury lamp and the UV LED as a comparison here. You can see that how small it is in comparison to the mercury lamp. However, there's a problem related to a UV mercury lamp. That is, the efficiency is still very low today. It's about 3%, converting electricity to photon energy, right? So, however, people have already started to use UVC LED for public space sanitation. So this is it's installation in a subway train. As you can see here, this is the air conditioning unit, and this is the inlet of air, and this is outlet. And then before the air flow into the subway train, it actually will go through the UVC LED array and get sanitized. And technically, because the efficiency is still quite low right now compared to the mercury lamp, there are many things semiconductor engineer and scientists can work on. And currently, my group and also many groups around the world are working on to improve the efficiency of the UVC LED. And it is predicted that by about 2030 or so, the efficiency of the UVC LED will match that of the mercury lamp. And so by that time, will be a great opportunity to phase out the mercury lamp that is not desirable for the environment. Yeah, and the last aspect of the UVC LED is that not only it can sanitize, surface, water, and air, but also it can address some of the food-related problems as well. As you know, almost half of the world's food is thrown away each year, right? And in the meantime, the food production generate about 1/3 of the global, greenhouse gas emission. So this can be a significant problems. And this is an experiment done by the US Department of Agriculture. And as you can see here, if you purchase fresh strawberry and if you just put it in the fridge for 9 days, you will have this fungus growth on the surface, right? So for most of people, we just throw away the strawberry, right? But that will result in food waste. But however, if you put the UVC LED in the fridge and after 9 days, it has no fungus on the surface and it's still as fresh as the time you buy it, right? So this can solve a lot of the food waste problem. So this is a great opportunity. So is there any KAUST student working on this? Actually, I was teaching a class, a course about the UVC LED about 3-4 years ago. And there was a female student called Asra, probably some of you know her. And she was very interested in the application of UV LED for food preservation. So actually, she decided to start a company on that. And last year, she was selected as one of the, I think, 30 under 30 by the Forbes Middle East. So she's working on this technology right now, and hopefully, she can make a lot of contribution to reduce the carbon emission due to the food waste. So here's a summary. I will do a summary for Thomas as well. So today we have talked about different technologies, especially the immersion technologies based on organic semiconductors and inorganic semiconductors. And the application of those immersion organic and inorganic semiconductors cover many aspects of the 17 sustainable development goals right here and also at the doorstep. And for example, Thomas talked about how to minimize the carbon emission from the manufacturing process, which is right here. And I talk about how to utilize UVC LED to cut down the food waste that can contribute to the zero hunger goal. So as the major physical foundation of the modern society, the semiconductor can do a lot more. Actually, at KAUST, we have about more than 20 faculty and more than 400 students, postdoc, researchers, and staff working on semiconductors. And so I highlighted the potential contribution of their research right here. As you can see here, they can cover most of the sustainable development goals. And with that, thank you for your attention. Yeah. Yeah. So Thomas, you.
Yeah. Okay.
Okay.
So from expert point of view, what will dominate the future market is going to be organic or inorganic semiconductor.
I think it's not going to be a single technology, but there's a lot of emerging trends, and some of these trends will be satisfied by these emerging technologies. For example, in the forum, Future of Semiconductors forum we had in Riyadh a few weeks back, we had one of the companies which essentially developed flexible microprocessors on foil. This can be done with silicon, even if you try very hard. So there's going to be another semiconductor technology. So we will see these products emerging and going in parallel with silicon. Silicon is not going to go anywhere for many years to come, but there will be a lot of other technologies that are coming into the market and contributing to a range of products. That's my view.
Yeah, I agree with Thomas. Right now, you can see both organic and inorganic semiconductor in the market. The major consideration of the choice of technology today actually depends on the performance and cost. But however, I think going forward, people will also look at the carbon footprint of different technology too. So I think if you use Google Flights to check air tickets, you can see that right now they actually provide for different flight options, they actually provide the amount of carbon emission for a specific flight. So I think going forward, many of the countries will start to implement this standard. So the end users will see not only the cost and performance, but also the carbon footprint.
I also to add that if you have an iPhone or a Samsung Galaxy, there's already organic electronics there. It's the organic display you're looking at. So you see this already penetrating the market, becoming an established technology. We see a lot of these kind of hybrid systems coming into play.
So Thomas, when you were bemoaning the poorer performance of organics, is it in terms of devices per area? Is it in terms of watts per flop? Is it in terms of accuracy, the reliability? I mean, there are many ways of that you might be implying, and I'm curious, as someone who uses high performance computing, when you sort of said organic technology is not going to be replacing silicon anytime soon, but where are the sort of performance bottlenecks in terms of those three or maybe other criteria?
Right, you're absolutely right. So if we're talking about light emitting lighting, for example, light emitting generation, organically it is already very efficient, because you don't need the electrical properties you will need from a semiconductor for transistor applications. So this is why we have OLEDs, organic light emitting diodes, in our phones, because they are 20-30% efficient in generating electrical current photons. But when it comes down to electronics, we face fundamental limitations. In silicon, we have silicon atoms connected with each other through very strong covalent bonds, chemical bonds. In organics, we have molecules, which the molecules with the atoms within the molecule are connected strongly through covalent bond, but the molecules themselves are electrostatically coupled to each other. And the charge to hop from one molecule to another, it's not easy. As a result, the current propagation through these organic semiconductors, which connects to the fundamental processes, is limited. So the speed with which these charges can propagate through the organic semiconductor is 1,000 times lower than silicon. What that means, it handles 1,000 times less power. It's 1,000 times at least slower. And this is where the challenge is. What we were trying to do is to make the device, critical device dimensions, smaller, so small, 10 nanometers, where this limitation is not applied. So what that means is that the structure becomes material agnostic, which means whatever you put there will be good enough for a lot of the applications. So very different approach to developing newer and better materials that conventional wisdom usually dictated progress in this field for the past 20 years. So that's our angle in a way, but that's a fundamental limitations. This a factor of 1,000 difference between silicon and organics. Yeah.
Thank you.
Has a question. Okay.
So in future, if I want to use inorganic device and semiconductor device together. So in most of the semiconductor device, there is a heating effect. So does that heating effect affects the inorganic devices also?
Yeah, absolutely. Organics, a lot of the inorganics, Professor Lee was actually talking about, they can sustain temperatures of several hundred degrees Celsius. Organics will not last that for such high temperatures. Essentially, will not be able to. They will melt away. So there is a finer window of operating a temperature that exists. We can easily go up to a few hundred degrees, but anything beyond that is actually not possible. And as a result, that directly relates to organic light emitting diodes, for instance. Initially, they were proposed for lighting application, but the gallium nitride came along and completely displaced hundreds-year-old technology, and organics were not competitive. Maybe one day there will be. There's a lot of progress there. But pushing a lot of light generates heat. The moment you have an inefficient light generation process, and that heat with organics is directly related to the degradation process. So this is a fundamental issue. It may be addressed in the future through material and device development, but this is a big difference from the inorganics, like gallium nitride. On the bright side, organics can be printed at room temperature, can be that do not require heat for manufacturing, only moderate temperatures, and as a result, energy. Gallium nitride, if you ever operated one of the machines, you will see how complex and energy intense the whole process is. And this is where the balancing comes. And we see that OLEDs are perfect for light display applications, maybe for many more microelectronics as well. There's a lot of companies trying to develop, but there's certain application where high energy and high heat is involved, where organics, I don't think will ever make it. Yeah.
I have a question from Zoom.
Oh, good.
Yeah, sure.
So from Kang, says, I have a basic question. Why the wide bandgap semiconductor devices generate less heat than the narrow bandgap semiconductors?
Yeah, right. I show a figure earlier. Basically, is a resistance compared to voltage. So for wide bandgap semiconductor compared to gallium nitride, such as gallium nitride, if you compare that with silicon, so at a certain voltage, such as 1,000 volts, its resistance is about 3 orders of magnitude lower compared to silicon. So we know that the amount of heat you generate during when the current runs through is proportional to the resistance. So because you have a 3 order of magnitude lower resistance, so gallium nitride and other wide bandgap semiconductor will generate less heat compared to silicon. Yeah.
I have a question myself. Very, very interesting talk, Professor Thomas, Professor Lee. Zooming out from this, we see the incredible work of increasing efficiency. Don't you think that with that we increase consumption and overconsumption? And if we claim to reduce carbon emissions at the end, are we increasing more of this so people use, like, maybe we're not solving that end problem that we're trying to solve at the beginning? I'd love to hear your thoughts on this.
Yeah, you're absolutely right. You have a growing market. You see these growing markets in different sectors, which are exponential. Makes you wonder. I remember when I was listening about when I was working at a company, and they were saying we're going to invest in LEDs, in organic LEDs, was up and coming. Back then, we only had fluorescent. Fluorescence is this light here, which still stand because they're very efficient. But the whole idea was that revolving around, okay, a huge amount of 30–40% of energy is wasted for lighting. If we can come up with something more efficient than the Edison bulb, incandescent bulb, will make a big cut in the power consumption. That hasn't happened. The end result is we have LEDs everywhere. Before we couldn't do that. The same happens with the flat panel screens, are more efficient than CRTs, but we have so many more now, yeah? And this, I think, is a problem that doesn't go away. I think the best we can do is to come up with technologies which are intrinsically sustainable and greener than the previous one. Yeah, with a positive, let's say, impact in terms of carbon emissions. That's my personal view. I don't see how we can circumvent the problem of growing markets, which is counterintuitive, but it is what's happening. We're improving efficiency, but we're deploying many more of these items, technological items. Yeah, I don't know.
Yeah,
have to add something.
yeah, thank you. Yeah, I agree with Thomas. I would like to add a small thing is that I think when the technology become better, people tend to have more, right? When we are happy with the 1080p display, and then we want to have 4K and 8K, right? Which we have more LEDs actually. So that is the issue. Actually, that has been the case for most of the semiconductors since the first transistor was invented. As the transistor become cheaper and cheaper and more and more energy efficient, people will buy a lot more. Okay, so as Thomas showed earlier, like by 2030, the Internet of Things, power consumption will be about 20-30% of the global energy consumption, right? That's huge. But I think like one thing is about the consumption. The other one is that what is the source of energy, right? So I think a lot of the company and the country are doing now is that they realize that they are going to use more and more energy for data center, for example. But they also announced that they have plan in place that will install as many renewable energy sources as possible, so that by a certain date they will offset the energy consumption. They will reduce to carbon zero, right? They will reduce from a carbon positive position to carbon zero. So one news I heard recently is that I think Microsoft has announced that by 2030 or by 2035, I forgot which year, the amount of renewable energy they install and they will produce can offset all the carbon emission since Microsoft was founded, right? So I think that the source of the energy, like Thomas said, like the solar panel, but also other renewable form of energy, wind, hydro, and others can help alleviate this issue.
Yeah, so this is a very interesting, absolutely question to the point. We have to, also ask ourselves and perform thought experiments. Imagine you had a technology. I show you, for example, some of these organic TVs. Why I'm interested, because we have to look at the boundaries, how good it can be. We know how bad it was. It took us 20 years to reach where we are. But how good it can be. It could be at the point where you have a desktop printer that prints your solar panel at will, enough to power your house one day. But right now, we know it can be done. Economics don't allow this because still the loss of scaling of production of materials is not there. Companies have not invested enough, but it's happening. But we're at the point also where the costs start being determined not by the active materials and the processing, but actually by things like substrate, the plastic we use to print them on. The encapsulation technology is more expensive than the whole material that we use to make these active devices. Suddenly other problems appear, and I think there are solutions, but once this solution will be addressed, we will come up with technology that potentially will allow all this room to be covered with a solar panel, so we can scavenge this energy with 40% efficiency and feed it back into that. But economically, this is not possible right now. It will be too expensive. But where will be the breaking point where essentially these conditions will be met, and technology, this emerging technology, be able to really have a massive impact, not just on a faraway farm that's hidden in a desert or in a forest, but actually on daily objects. I think this is, we will see convergence, this technology coming together and really providing solution. But we have to have a vision, we have to push for this to happen. And I think the scientists are there to make the technologies better, accelerate the pace with which progress has been made and reach to the magical point in the future.
Thank you so much.
I think we have two more questions. Do you have questions?
Thank you for the wonderful talk. I like to see this final slide. I go for more practical question. We are now in the process, as being announced by our president, to think of our climate commitment for KAUST. So hopefully in the next months, we will having enough space for debate of what we're going to be our actions. And my question to both is, under your research, if you were able to deploy in the campus your research to help us towards a specific climate commitment that hopefully will be before carbon neutrality by 2050. I hope we go before that. What it would be? Do you have already something that could be deployed and could be 10 years, less, more, and what areas, and in terms of outcome efficiency, what are you expecting?
That's a very tricky question. We work with partners companies that are producing technologies like the building integrated PV. I think this is a great opportunity for Saudi Arabia, considering that 95% of the components that goes in these printed PVs are essentially plastic, or petroleum products, but used in a different way and can be recycled and can be reused. So we've been talking with companies, well, what can we do? And of course, companies are there to sell you things. Is the level of maturity of this technology at the right place? No, they do cost a lot of money. But the proof of concept can be demonstrated at a cost. If this is not an issue, then I think there are solutions where you can have pilot projects where you really see how these technologies can help us. For instance, having a semi-transparent, a beautiful kind of solar panel on your window, I wouldn't mind. I have prototypes in my office. You see, they're very beautiful, devices. But that will block some of the heat that's coming into the buildings. My building is facing my office facing the sea, and every afternoon is like an oven. The air conditioner blows, and it's a kind of I can't have a Zoom meeting because the air can keep blowing cold air. So blocking some of the heat will minimize the need for air conditioning. At the same time, generates electricity. There are studies performed. There are tremendous benefits, but the cost of the solution is still high. That's the problem. But we can think of examples, how we can deploy, how we can test these technologies in the field. Because if you look, for example, Saudi Arabia, there's not many, it's a perfect place in the world. We have double the amount of energy per unit area compared to anywhere else. That's pretty good. And we still have to learn how the different technology will perform here, renewables such as photovoltaics. So there is a lot of things we can do there, and a lot of things that can be tested in a larger scale, not just laboratory scale devices that we've been doing. And within the Solar Center, we've been doing exactly that, trying to assess the performance of different technologies and work with partners and have access to larger size prototypes or even products, which can then be assessed under realistic conditions. So there are some possibilities that we can discuss the details later on, for sure. Maybe.
Yeah, thank you for the question. And so to reach carbon neutrality, I think one thing is that we need more and more renewable energy. But for my research, I'm not working on solar cell. However, I'm working on how to reduce the energy consumption of technology, including electric cars. And taking the power electronics as example, the goal is to develop the conversion efficiency, right, to about 99 to 99% in the next 10 years or so. So meaning from AC to DC or DC to AC, right? You saw a lot of this conversion in an electric car, for example. But there are a lot of those conversion in the air conditioning unit as well, which I believe is a major consumption of energy at KAUST. So I think what if we realize that, we can definitely help the community, but also the entire global community to reduce the energy consumption of those key technologies used in life and in manufacturing.
Thank you, Professor Thomas and Professor Xiaohang, for your interesting talks and also for our audience for their questions. We would like to continue.
Homemade in the core lab class.
Oh, wow, nice.
Yeah.
Yeah.
Thank you. Thank you very much.
Yeah, thank you.
From our canvas, you know.
Oh, wow.
All right.
Your desk.
That's cool.
And remember us from
Oh,
there.
thank you.
So much.
Oh, nice.
you.
It's
For
a
the audience.
reusable top.
Yeah, sure. Thank you for speaking with us.
My iPhone is good enough.
Thank you very much. Yeah.
Great. Thank you.
Thank you. Thank you.
Jen.
Thank you for the invitation. Yes.
Oh yeah, it'll be good.
And this